All right, so we have a demonstration. We're going to begin class today with a demonstration of the photoelectric effect. So just to remind you, the photoelectric effect does not demonstrate, it's not the first experiment to demonstrate that light is quantized. You'll frequently read that, like in Wikipedia, it's incorrect. The photoelectric effect demonstrates that the electron states, at least this much, that the electron states are quantized and that there's an energy barrier that the electrons have to overcome to be pulled out of a piece of metal. In this case, we had zinc. Is this zinc as well? This is zinc. Zinc is nice because the gap is called the work function, the energy required to pull an electron out of the metal. The frequency, remember the demonstration that this energy is overcome by the frequency of light, not by the intensity. And so this energy is low enough for zinc that we can use a relatively safe light source. So for most metals, this light is in the UV range, and so you don't want it to be too high frequency because that can injure your eyes and so forth. So to make it safer, the other reason we use zinc is because it can be cleaned. You want to get rid of oxide because that changes some of this results. You want to. He was using sandpaper to scour off the oxide of zinc, and zinc oxide is not very thick. So unlike iron, for example, where the oxide continues to grow through the metal, so we choose zinc for these reasons. And he's charged up the electroscope here through the triboelectric effect, which is just rubbing one material against another, and you want to choose the materials correctly so that this is negatively charged now. And so now he's going to, I'll let Dr. Thompson go ahead from here.
All right. Yeah, I'll see if I can get a little more there for you, hopefully. Yeah, that's a little bit correctly. All right, the humidity helps it leak out a little bit too. All right, so we got the UV light there. That's the longer wavelength, easier for you to see, right? But the parties. You got the even worse for your eyes right there. Hopefully not too nasty. Hopefully. Close. A little bit of drop. See if I can make this side better. Fine, directly over. It is directly forward. Not that big of an effect there. Only I pull that through. Well, on one cell.
So to remind you what's going on, the electrons are mobile. There's two kinds of charges. We call them plus and minus. The electrons are mobile in the metal. And so when the electrons get deposited on here, they spread out. They're repelling each other. They spread out. And that's what causes the electroscope to push itself open, right? Because the mobile negative charges, they want to try to get away from each other, so it creates a force between the leads of the electroscope. So having the electroscope, that little lever, handed over means there's charge on it. And he's trying to get rid of the electron, the excess electron charge, by shining the UV light to eject the electrons off of the zinc. You can see the challenge for doing electric experiments.
Yeah,
because it's greatly affected by humidity in the air. Makes it difficult to control.
This one's probably getting utilized in the sunlight too.
Oh, yeah.
It's getting treated already.
Can we maybe let's try closing the blinds in the back, please, guys?
Bring it back and I get it on.
There you go. The other way. Okay. All right.
The sun doesn't prove a point, eh? This helps prove it too, eh? That one doesn't have zinc on it. I don't want those. Be better HD. We should go do this in time.
I get the transfer. This balloon is charged, but it's not transferring.
Yeah.
That's the tricky part. Maybe the lucite rod would be better. So
yeah, next time. Just try to bring it.
Okay,
Oh, wait.
all right.
Man, it was so cool.
You got it to work before the class.
Yes,
Before
sir.
the class.
It was so
All Friday.
amazing.
That's what experimentalists always say.
It worked one time. Let's publish.
I'm sorry.
That was a good one.
All right, yeah, I don't think we're gonna get there.
Okay,
I'll move on.
well, this is easy enough. Maybe we could try it again.
We
Next class. That was great. Okay, maybe using a new site rod to.
Oh, there we go.
Oh,
Oh, yeah.
it's
It's very small.
We got one student.
right down in the front row.
They can publish our results. I'll move on then.
Try again. I think the transfer is easier with a new site rod.
I think you're right. Wrong.
Yes. There you go. There you go. I got it. A little bit.
A little bit. And then let's see if we can free
Yes,
it.
sir.
With the little pendulum
Yeah.
type thing, what are you guys trying to do with that?
Okay, so the electroscope has two pieces of metal. One is fixed, the other one is free to rotate, and they're connected to each other. When you transfer negative charge to the metal, then it's going to spread out. The negative charge is mobile and wants to spread out, get away from get away from each other. Well, there are negative charges on both of these pieces. The negative charges along here and negative charges along here. And it's going to push this away, produce a torque. So that thing being not vertical, the rotatable piece, the second leaf, when it rotates, that indicates that there's charge present on the electroscope.
That's positive charge going out.
Well, yeah, but that
Doesn't do any good.
that doesn't do any good for this. Okay, so we got a negative charge. Can you see the leaf now is tilted some? That indicates the electroscope has charge on it. The trick here is to make sure that it's negative and not positive. So now we have excess electrons on here. And so if we shine the UV light on the zinc, electrons would then be stripped off of the zinc by the light. And so that'll reduce the negative charge on the electroscope. So got a charge. Want to try again? With the
Oh,
light?
that's positive charge.
Okay.
Just the negative charge is kept escaping. Positive charge.
Now, you see why it's not going to work with this positive charge. You're just making it more positive to charge.
So we push it.
It would increase the angle. So that might show up some.
That's also approved, right?
And that would be a way of charging the electroscope. It's just a final.
Oh, yeah.
Well, thank you very much. We'll give it a try. I think that's a good one to try again.
Try again. We'll try it.
Okay, Bragg, second fail. What's the second fail we have?
Whoa, wait.
What are you, 3 for 5?
Oh, kill me.
Oh, that's pretty good if you're playing baseball.
You're playing baseball. Don't tell Don Trent, I guess.
Your guys. Thank you, Dr. Thompson. So what was there a question? Okay, so we're working with complex numbers, complex variables. And the goal here. So I wanted to complete my thought on that. So the photoelectric effect is often cited as an example of proving the quantization of light, but that's not true. It proves that the electron states are filled up down to some low level and they need to be brought up to a higher level. The quantization of light is not proven until you get to Compton experiment in the 20s. The photoelectric effect was decades before the Compton experiment. And Einstein was running around for 20 years saying he was convinced that there was something like quantization of light. And he wanted experimentalists to devise some means of proving that. And it wasn't until Compton in the 20s before that was really done. Quantization of light is a subject we won't study in this class. We're going to focus on the first effect, which is the quantization of the electron states in a metal, for example, or in the atom. And so this course, ordinary quantum mechanics, is called, really has to do with that, the quantum nature of the electron or other massive particles that constitute substances, elementary particles, or the behavior of these virtual parts in a metal. Quantization of light is left to another subject, that's quantum field theory. the development of quantum field theory took decades, even after Thomson's experiment. It wasn't until the 50s, really, before we had a reasonable quantum theory of light. And there are various mathematical problems that crop up. And it was Feynman and others who developed the quantum theory of light, and that was what he got the Nobel Prize for. So we're not going to do that. It's a difficult subject for various reasons, but we're going to focus on the quantum nature of the electron. Okay, so my promise is that these complex variables are going to provide a compact and convenient way of describing wave motion. We're going to be developing a wave equation, the Schrodinger equation, and it's it's normally written explicitly uses I, the square root of -1, as the formulation of the wave equation. So you don't have to do it. You can do it without complex variables, but it's more complicated. So the complex variables provide a way of doing a very compact solution. Engineers, double E's, use complex variables all the time in the study of oscillating circuits, AC circuits, for example. And they call them phasors, I guess. Commonly complex numbers. Okay, and we had the famous Euler relation. The exponential of a purely imaginary argument, so theta here would be considered to be a real variable. And e to the I theta then is related to these trig functions. Cosine and sine. Yes, sir.
This is all relying on polar coordinates, right? Like the polar coordinate system.
Well, no, not necessarily. So theta could be the angle of a complex variable. Could be that. But this is a general relation. Whatever theta is, it's a real variable. So it could be, for example, we're going to write a function of time. So it's not an angle explicitly. And we have then this omega t is like an angle, but there may be no angle actually involved. The oscillatory motion. Now let me just work on this, and we'll come back to the connection between this relation and why it's kind of funny, because it looks like there's an angle involved. So we'll come back to that. But I want to point out here that if I flip the sign, SIGN of theta, or take the complex conjugate, you see my problem with when I say sine? Yeah, okay. So that's why I talk about the SIGN, SIGN. Okay, if I take the complex conjugate or flip the value, flip the sign of theta, SIGN of theta, let's add, I get the complex conjugate, let's add these together, and the imaginary parts cancel out. So I can add these together and show cosine is the sum of two exponential functions like this, complex exponentials. And likewise, the sine of theta, if I now multiply, let's see, I want to subtract these two equations. Subtract this from this. And I get this. And we'll make use of this quite a bit. Okay. And in this, also, you may want to write, remember, 1 over I, maybe more convenient to write this as negative I. I is the denominator. Frequently more convenient to rationalize it, speaking like we were talking about other kinds of numbers. 1 over I is like negative I. All right, so I demonstrated how to solve quadratic equations using complex numbers, getting a general complex solution to a quadratic polynomial. And I pointed to the general fundamental principle of algebra, which is that for a higher order polynomial, say an nth order polynomial, they're always in roots, which may be complex, cubic or quartic or so forth. We'll have higher order, more roots, but they can all be written as complex numbers. So that's an immediate application in terms of algebra. But we're going to be applying this now to the solution of a particular kind of differential equation you studied some, a particular kind of equation that you studied some, which is called a differential equation. So let's look at this function, f of x e to the ax. X derivative a e to the x. Right? And the second derivative then would be a squared. Okay, so let's suppose I have an equation that's of this form. F prime of x is equal to b f of x. So we're going to be working with systems of equations, differential equations with initial conditions. So in other words, this equation must be true for all x. So what we're looking for is a function. We're looking for f of x, whose derivative is proportional to its value. And so unlike an algebraic equation where we're looking for specific numbers to solve an equation, here we're looking for a function. And that's how differential equations are distinct from what you've done before with algebraic equations. And this places a condition on the function. So we'll find that this has a whole set of solutions. And solutions of an equation like this can be specified by specifying the value of the function, say at x equals 0. Okay, well, looking over here, it's easy enough to guess the solution to this really simple equation. This one's easy enough. We could say we could guess something of this form. So we're not going to cover solutions of differential equations in this class, other than generally for the most part, I'm just going to say, try a solution of some form. And so what I want you to do is to guess and check. So you're going to take a course, if you continue doing this, you'll take a course in solving differential equations. We're not going to cover the subject of solving differential equations. I'll give you some solutions. Very often you can kind of guess at what the form ought to look like based on what kind of physical system you're looking at. And then I want you to check by substituting this into these two conditions. So there's the differential equation and the initial conditions. Okay, so I'm going to check. So I want to find, are there values of big A and little a that will match those two conditions? This really simple example. We're going to get into some more complicated examples. I just want to show you the principle involved. Okay, now I can't just integrate this equation. All right, this is why I can't directly integrate. Because if I were to integrate the left-hand side to get f of x, I'd have to know f of x to integrate it. So this one is not one I can solve directly. So for example, here's another differential equation. Let's do and I want f of 0 is equal to f0, and f prime of 0 is equal to the value. Okay, so here's another set. First one is a differential equation. Says the second derivative is constant, independent of x. And I'm going to choose two values for it. You'll find out that the order of the differential equation of a simple differential equation, a linear differential equation of these types, the order determines how many initial values you specify. So this is a first order equation because there's a first derivative. Second differential equation because there's a second derivative. So this is second order, which means I can specify in usually two values independently of each other. Okay, so an example of this would be, physical example is, I take a body and I let go. Or I could give it some initial upward impetus or downward impetus. So I have some initial conditions. Starts off some initial height above the floor, and its initial velocity is determined by its initial impetus. Yes, sir.
What's the two dots? Is that? prime?
Yeah, so physicists use dots to indicate derivatives with respect to time. It's a convention, so anytime you see dots, so generally we use primes to indicate derivatives with respect to other things. And so this is a y double dot of t. Okay, so this is an example of this. We can cancel the m's. We have an example here. The second derivative is a constant in time. So we say loosely that the acceleration is constant, right? And we've been through the physical explanation of this with the impetus and the force and so forth. Now we're just looking at it mathematically. Okay, this is an example of an equation. This is this one, which I can integrate directly. So I can integrate y double dot with respect to time from some time to a later time. Okay, now the argument of this integral is a constant. I know what it is. And so by the fundamental theorem of calculus, integral of the second derivative is derivative evaluated at the endpoints. And this is I know what this is, so I can integrate this portion of the time. So let's solve for y dot. And the initial value of y dot is the velocity. Okay, and now I integrate again. First derivative. So I integrate both sides, left and right hand side. I'm running out of chalk pretty quick. And again, this integrand is known, right? It's a linear function of time. And I can do both of these integrals. Okay, and this gives the integral of the derivative gives me just the difference in the function of the two endpoints. And this is specified as the initial height. So then this is the formula that you've seen, h plus v naught t minus 1/2 g squared. Okay? This one you can integrate. Just use ordinary integration to solve. This one you can't. I can't integrate this one. Why is that? Because I don't know what f of x is yet. If I try to integrate, I can, the integral of the left-hand side will give the function difference in the value of the function, but I don't know what f of x is, so I can't integrate it. So I can't do direct integration, at least in this simple way, with an equation like this. And this is more like what we're going to be studying. Okay, so you see why I have to resort to more advanced methods for solving differential equations. We're not going to cover that in this course. I'm going to give you something to try. Just guess, okay? Guess and check. Okay, this is what I want you to, this is the guess I want you to check. So how do I check whether it solves this system? Well, the first thing is I could just evaluate it at x equals to 0. So that immediately gives you the value of a. It's the initial value of the function. Value of function is 0. Now, so I got this. This is good. Check here. I have to take this function and substitute both sides. So I need to take the first derivative. And now I put it on both sides. And now this must be true for all values of x. Okay, it's maybe more convenient to pull the right-hand side over to the left-hand side and factor out the terms. Okay, and we found out that capital A is not 0. It's whatever value of f naught, whatever the initial value is. So capital A can't be 0. E to the bx is not 0 for general values of x. So it must be that what's in the parentheses must vanish. In other words, the A here must equal this b. Okay, so the complete solution then for this problem that matches both the solves the differential equation and matches the initial conditions. That. You see how it works? Let's try this solution. I'm going to try this one. It's not the right, it's not going to work. Let's see what happens. Let's see what goes wrong. If I give you a function that isn't a solution, you should find out that it doesn't work. How do we do that? Okay. So another guess would be f of x for a plus bx plus cx squared of this form over here. Let's try this. We should find that it doesn't work. Okay. Well, how do we do that? Well, let's check again the initial value. Well, that's a. So let's set this big A just equal to this little a equal to the initial. I'm sorry, the initial value. That's null. Okay. Got that much is going to work. But now let's try the differential equation. So we need to take the derivative of this. And then we need to substitute these into the differential equation, left and right hand sides. So the left side is b plus 2cx. The right side has to be, oh, I've got too many b's here. Hang on. Sorry. Not writing in ink, are you? Let's do that. Okay, and we established that big A is F null. Okay. Can we find some values of big B and big C that will make this true for all values of X? You see, it's not going to work because I have no X squared on the left-hand side. I've got to match it to the X squared on the right-hand side. Okay, so that would mean, well, C has to be 0. See why? We have a parabola on the right-hand side, but we've got a line on the right-hand side, which means we have to force the function to have no curvature. We got to get rid of c. C is equal to 0. Well, if c is equal to 0, it's also 0 here. Now we got the same problem. We've got a constant here and a linear function here. Is it going to work? Now we got to set b equals to 0. We've gotten rid of everything, right? It can't work, can't match, because now we have 0 on this side and we have something not 0 on the right side. There's no way to make this work. Yes, it's right.
Back on the original. How did E go to the BX there? Would it not be A?
No, this was the equation. So little a was a parameter yet to be determined.
Yes, sir.
So in this guess, we have two parameters whose values are determined by making it solve this equation.
Yes, sir.
So little a must be equal to this value, which is given in this equation. Okay.
So, but I thought you're supposed to take that and plug it into that differential.
Right. And the only value for little a is b. This is the only way. This is the only function that will solve the differential equation. So I did the substitution. I should put that not here.
So my confusion is when you go to the right below, 2 lines below A equals F naught.
Right here.
Big A, little a, e to the dx equals that. I'm just curious what happened to the A.
Right here.
The
Okay,
AX.
I pulled it over to the left-hand side.
Oh, I'm sorry. What happened to the e to the ax? Because that's what you plugged in originally for f of x, right? E to the big A, e to the
Oh,
ax.
I'm sorry. You're right. Excuse me.
Yes, sir.
Don't know little a yet. There we go. Thank you. I'm sorry. Does that help?
Yes, sir. That clears the confusion.
Thank you. I jumped ahead. And you could go ahead and substitute here as well the value F naught for big A, if you like. So determine what big A had to be. Okay, it's a very simple idea. I just wanted to demonstrate it in a really simple case. And because we're not going into how to solve differential equations in this class, we're going to be doing things like this. Try this and tell me if you can choose parameters in the guess that will make it work as a solution. Okay, there's a beautiful subject, differential equations, how to solve, what kinds can be solved and how to solve them. We're not going to do that right now. I'm just giving you some guesses. And usually the guesses will be physically motivated by you have some idea about what the thing should be doing. Solution should have some kind of characteristic. So the guess will reflect that. Okay. It's a really handy way of doing things, but it's great to be able to develop the muscles for actually techniques for solving these different equations in general. Okay, so do you get the general idea? Is everybody okay on that general idea? Yes, and check. All right, so let's try this. Let's try something a little more robust. Oh, yeah, the other point is I want you to see why what you're familiar with here can be obtained by direct integration doesn't work for the kinds of differential equations we're going to be trying. Like we need. Just direct integration is not going to work. Okay, so now let's try something of this form. Let's do a simple harmonic oscillator. We've got a mass on the end of the spring. Constant K. At some point of equilibrium, we mark our displacement relative to the equilibrium length of the equilibrium point of the spring. And so if we pull the mass off from equilibrium, there's a restoring force that tends to pull or push the mass back to its equilibrium point. So the spring is neither extended nor compressed. And using Newton, so we could say that the force, according to Hooke's law, is negative kx, where k is the spring constant, and x is the displacement from equilibrium. So if x is positive, you pull the mass to the right, the force is back to the left. The spring has been stretched, it's trying to pull it back. If x is itself negative, then the spring is compressed and it's pushing back. And so this, if x is negative, this is positive. The force is to the right. So everything works in a very compact way, both compression and stretch. Okay, so let's write down Newton's second law for this system. There's a differential equation we want to solve. This is a simple harmonic oscillator. And we have a choice in most physics problems of this type. We can specify the initial displacement and the initial velocity. Specify two. The second order differential equation, because there's two time derivatives here. And so there are two initial conditions. And notice that those initial conditions can be specified independently of each other. All right, what does that mean? Well, I have two choices to start it off. One is, well, where does it start initially? And the other is how much impetus it has to begin with. I can set those two things up separate, right? So I can give it some initial stretch and then I kick it to get started, right? So I'm specifying both the initial position and the initial velocity. That makes sense. There's two. This is a really important point in physics. That the two initial conditions are independent of each other. It's like here. Okay, I can specify the initial height, but I could also give it some initial velocity. Could be up, could be down. Could be zero. But I can change the height, but keep the initial velocity the same. I have two constants I can specify. This is really important. Simple point, but really important. Okay, so I have to specify to get a complete solution, both the initial position and the initial velocity of this mass. So here's my system. Mathematically, now I have a self-contained thing. Empiriometrically, I have reduced the physics problem down to just a math problem. That's the goal of the empiriometric, is to have a self-contained mathematical system which answers certain kinds of questions. And so that's the goal here, is now I've got it expressed mathematically, the rest is just math, right? Okay, and as I said, you can't just directly integrate this, because I can integrate the left-hand side, but I don't know what x of t is yet. And solve it. So I can't, by just straightforward means, do this by direct integration. Guess and check is coming, right? Okay, well, let's try something like what we did over here. I'm anticipating the initial conditions. So I've already met the initial conditions here. But if I substitute this into here, it isn't going to work. You can't get a solution for all time. That will, can't get an x of t that will match this condition where its second derivative is proportional to the distance. It isn't going to work. Right? Because we have, when we take the second derivative, we'll just get a constant here. And then x is not a constant. So there's no choice of c that will work. So this fails. Doesn't work. Usual kinematic equation does not satisfy the simple harmonic oscillator. Okay? Okay so far? Let's try another one. Another guess. Let's try that. Okay, now my guess is motivated by the fact that I know the solution. And I know this relationship. Now this is going to work out here. There's going to be, we'll see what happens. This works. Let's see if we can prove it. So I need to match the initial conditions and the initial velocity, right? Okay. But more importantly, before we get to that, let's substitute this into the differential equation. Let's look at that piece. So I need to take two derivatives, because I need x of t on the right-hand side, and I need x double dot on the left-hand side. So I need to get, if x of t is of this form, I need x double dot. So x dot is ab e to the dt. X double dot ab squared e to the dt. Okay, it's looking promising now. Let's substitute x double dot and x of t. And again, it may be convenient to bring over the right-hand side to the left-hand side, so we set it all equal to 0. Is that an O? Somebody saw it? Somebody see where it's going? I'm going to factor out common factors. And in order to match the initial condition, big A can't be 0. You can see here if I try to match the initial condition, in fact, big A must be the initial value of x. So you can see the big A in general is not 0. And e to the bt is generally not 0. Right? So the only way is to make that parenthesis. The thing in parentheses has to vanish. And then I have a function that has the right dependence. The second derivative is proportional to its value. Okay, so mb squared plus k is equal to 0. Oh, look what happened. We transformed the differential equation into an algebraic equation. We're solving this for little d. There it is. Okay, so notice we have transformed the differential equation into an algebraic equation for one of the parameters in the guess, in the purported solution. of that thing. Okay, so let's solve for b. This is the quadratic equation, right? We have a negative discriminant, which means that B is going to be imaginary. So this K over M is related to the frequency of the simple harmonic oscillator. Remember, in your study of the simple harmonic oscillator, in introductory mechanics, this mass will oscillate with a frequency that is the square of which is K over M. And this is coming out here. So K is positive, M is positive, B squared is negative. B is pure imaginary. So B, there are two roots to this equation. Remember that for quadratic equation, there are two roots. Discriminant is negative, so it's actually they're complex roots, and in fact, in this case, there's no real part for B. Okay, so I get this, and I'm going to write this in ordinary form or familiar form. We set omega is equal to the square root of K over M. That's going to be the frequency of the oscillation. The oscillation of this mass, the frequency of which is determined by the combination of the mass on the body, of the mass of the body, and the spring, the stretchiness of the spring. If it's a stiff spring, K is big. Gives you a high value of omega. If the mass is big, then it gives you more resistance to the impetus. Frequency goes down. Okay, so I have two roots here. Okay, all right, but now I'm a little concerned, right? Because I've got a complex function. I said B must be pure imaginary. If I come back to this, B is pure imaginary, which means the exponential of it is complex. How can I have an X, a solution, which is complex? That can't be, because it would mean the displacement has an imaginary component that doesn't make any sense. Well, it looks like we've got ourselves into a quandary because we've got a solution that can't be admitted for a physical system. But there is a way around this. Okay, so hold that thought for a minute. We're looking for solutions. Where B is pure imaginary. And so it seems like we've got parts that are correct because we'll have a cos omega t and we'll have a sine omega t. Okay, which looks like the thing is oscillating in time and the frequency is right. So how does this work out? Okay. So I want you to know that equations of this form are called linear equations. That means that X and its derivatives occur only on the first power. So there's no X squared. There's no X times X dot, because that would be second order in X. So everything in this equation is first order in X. Okay, and so we have two different solutions here. We have an e to the I omega t, and we have an e to the minus I omega. Both of them are possible solutions. So we form something that looks like this. E to the I omega t is a solution, so is e to the minus I omega t, and so is a linear combination. This is a solution to the differential equation, which you can demonstrate by substituting these two parts together here, and there will be one part on the left-hand side which corresponds to this, and one part on the right-hand side which corresponds to this, and those match. And then on the left-hand side, you'll have a part that corresponds to this, and on the right-hand side, you'll have a part that corresponds to this, and those match. They match p-swaps. Make the whole thing zero. Left and right-hand side will match. Okay, and that's because the derivative is linear, meaning the derivative is proportional to x, the second derivative is proportional to x. So x dot you see how it just brings down a factor of omega or minus omega? But it's still linear in x, second derivative, x double dot. Now minus omega squared, a plus e to the I omega t. And then I bring down a negative I omega, combine it with this. So I get minus I omega squared. Gotta simplify that. What does that come out to be? So I can pull out the omega here. What is negative I squared? Negative 1. Okay, so notice the second derivative here, there's a plus sign, and when I take one derivative, there's a negative sign, take another derivative, and they're both negative. I get the same negative omega squared. So I'm going to pull that negative omega squared out. And then this thing is just xt. So I get overall, this is negative omega squared xt. Okay, see how it's going to work now? I substitute this into here, and then I substitute xt into here. Okay, so I get then xt mx double dot. Okay, so I substituted in for x and for x double dot. Okay, now this is the same on both sides. So I could pull it over to the right hand side. I would have k minus m omega squared. And I have this stuff. This thing is not going to be 0 in general because x is not 0. So I must have this. Okay, so I got, in other words, what I said we find over there. So it works. Okay, so I'm just checking again a second time. Now, what I haven't done is match to the initial conditions, and I still haven't satisfied, I haven't told you how I'm going to get around this being complex. There's going to be no complex part left, no imaginary part left over. Like that. Even though I have, along the way, what look like complex functions, combination of two complex functions. But remember, I added e to the I theta and e to the minus I theta, and I got cosine. Right? And I took a difference. So what are a plus and a minus? They're complex numbers also. So I have to have complex numbers here for a plus and a minus so that the whole thing comes out real. And it all works. So let's see how it works. Okay, so we've got this. Can I erase this part? Okay. What? Yes.
Would that be a contradiction?
Why?
I thought earlier we thought omega to be the negative.
No.
Oh, no. Oh, I apologize.
Okay. Okay, so now we need to match to the initial conditions. We're going to use the initial conditions to determine what a plus and a minus are. And then we'll find out the whole solution is now real. Everything works out. So the initial condition, remember here is x of t. So let's find x of 0. A plus a minus. Right? Two exponentials evaluate 1. And well, that's the initial position. And then let's set this to 0. initial velocity. Again, we've gotten back to algebraic equations, two algebraic equations, linear and two unknowns. So we solve these two equations for A plus and A minus. Let's see if it's easy enough to do. So let's multiply the top equation by I over A. These two equations, we add them together to get A plus, and we subtract them to get A minus. So we add them together, and the A minus terms drop out. Okay, so A plus minus I V naught over 2 omega plus X naught. X naught over 2. Complex number. Real and imaginary part. The real part corresponds to the initial position, the imaginary part corresponds to the initial velocity. A minus is the complex number. Just flip the sign of the imaginary part. Flip the sign. Yeah, flip the sign. Is that right? Yes. Okay, so now we gotta do a little bit of algebra. We gotta substitute to finish up. Substitute these into the equation, into the expression for the solution. I'll show you what it works out to be, keeping in mind that these complex exponentials are related to the sines and cosines from the Euler relation. Altogether, it works out like this. Oops. That's it. Seems like it took a long way to get there. Right? Perhaps you remember this solution from your introductory mechanics in the first semester. Probably written down. Here's the solution. I'm showing you how to get it. By the way, the simple harmonic oscillator occurs throughout physics in one form or another. That is what I mean. Is that the differential equation occurs time and time again. So you should spend some time becoming very familiar with that differential equation. Sorry about that. Held you over a little bit. I'm going to start the next class by telling you that you should really become familiar with the simple harmonic oscillator mathematics and the simple harmonic oscillator and different methods of solving. Yeah.
How do you know?
Let's see, are there any questions from anybody else? I'm up to the picture of it here. Okay. So see you on Wednesday.